So today we're going to be doing 8.2, which is going to be probability of compound events. So this is more than one event happening, either at the same time, one or the other, and then one thing happening and then another thing happening. So probability is the numerical measure of the likelihood that some event will occur. So there's a range of probability, 0 being that the event is impossible, and 100% meaning that it's certain. So if I'm 100% sure something will happen, it's going to be certain that it happens. And the numerical equivalent to that would be the probability is 1. Okay, so your probability can be represented as a decimal, a fraction, or a percentage. The probability of something happening equally likely to things happening is 50-50, right? 50%, 1/2. So most probability falls somewhere between this spectrum. Now, your probability can never be less than 0, because nothing can be less than impossible, and your probability can never be more than 100%, because probability, it's not like something we can calculate over 100%, right? If it's 100% certain, you can't go above that. And then there's what we call a trial, which is a single random action done in anticipation of a result. So when you do a trial, that's like flipping a coin once, okay? The outcome is the result of a trial. So if you flipped a coin and you got heads, that would be your first outcome. And then a sample space is the set of all the possible outcomes. So if you're flipping a coin, what are the possible outcomes of that? Heads and tails, right? So that's the sample space, that's the possibility of the different outcomes. And then the experiment is the collection of trials. So that's where you do several trials and collect the data. So we'll look at an example. A coin is tossed twice. Each toss is a trial with an outcome equally likely of heads or tails. Together, the two coin tosses represent an experiment, and the sample space of the two coin tosses consists of 4 possibilities. So if you flip a coin twice, there's only 4 possible things that can happen. Okay? You can flip a head and then a head. You can get tails and tails, head tails, or tails heads, right? Those are the only 4 possibilities. So that's what we call the sample space. And then as you keep flipping the coin, you're going to have a larger and larger sample space, right? Because more possibilities can happen. So there are several different types of events. There's a simple event where only one possible outcome exists. There's a compound event, which is more than one outcome exists. 2 or more events will be linked by the word and or. So it's very important that we know the difference between and or, because they mean very different things in probability. And you can think about it this way. If you say, I want Nike shoes and Adidas shoes, or if you say you want Nike shoes or Adidas shoes, which one's more likely going to happen? Having just one, right? Being okay with one or the other is more likely to happen, right? It's a lot less likely that you're going to end up with both things. You're like, I want exactly both. That's an and. So the and probabilities are always smaller probability chances than or, okay? So that's the way I usually think about it. So then we have a mutually exclusive event. When 2 events have no outcomes in common, the events are disjoint, meaning there is no overlap in the events. So if A and B are mutually exclusive events, then the probability of A and B is 0. So inclusive events are when events have at least one outcome in common, they are overlapping. So you need to determine whether 2 events are mutually exclusive before you can find their probability. So we'll talk about some examples of mutually inclusive and exclusive so you can see the difference, because I think the examples are really the best way to understand this. So now we're going to talk about the probability of A or B, so events happening, one or the other event happening. So I'll zoom in here so we can get a better look at this. So we have mutually exclusive events. These are events that can happen that don't affect each other, okay? And when we have the probability of those that we want to find, we're going to add those 2 probabilities together. So, what is the probability of drawing a king or a queen from a standard deck of cards? Well, what is the probability of drawing a king? Anybody know how many kings are in the deck?
4.
Good. So 4 out of 52, you have a 4 out of 52 chance of drawing a king, right? Plus, you're okay with also drawing a queen, right? So plus we have the chance of drawing a queen, which is also what?
4.
Good, 4 out of 52. So you're okay with either one of these events happening, meaning your chances are going to be better, right? If you're more open to more options, you're going to have a better chance of what you want. So we add these 2 together, when you add common denominator fractions, you just add the numerators and keep the denominator. And this fraction reduces to 2 over 13. And if we actually calculate that, you have approximately a 15% chance of one of those two things happening. So you increased your chances because you're okay with more than one outcome. That's kind of the idea. All right, so let's move on to the next one. The next one is going to be baseball cards and hockey cards and stuff. So we have a stack of 5 baseball, 10 hockey, and 15 basketball cards, and they're shuffled face down. What is the probability of randomly selecting a baseball or a hockey card from the stack? So let's first do baseball. So what's the probability of selecting a baseball card? Good, 5 out of 30. 30 is the total number of cards. You have to add it up. And then plus, we're okay with also getting what kind of card? Hockey. What's the chances of getting a hockey card? Good, 10 out of 30. So we can add these two together. And we get 15 out of 30, which is? Good, 1/2. And that's because baseball and hockey cards make up half of the cards in the deck. Or in the pile, however you want to say it. Which means you have a 50% chance of getting at least one of those two. So any questions on the first two? Okay. So now we're going to move into mutually inclusive events. These are where events can overlap sometimes. So what is the probability of drawing a king or a diamond from a standard deck of 52 cards? Why is it possible these events can overlap? You can get a king of diamonds, right? So the way we do this probability is we find the probability of the first thing happening alone, probability of the second thing happening alone, and subtract away the probability of them happening simultaneously. So first, what is the probability of drawing a king in general? 4 out of 52. Plus, what is the probability of drawing a diamond in general? 13. So in a deck of cards, in case I'm assuming you know, but I shouldn't. Deck of cards has 4 of each type, so like king, queen, 10, and then it has 13 of each suit. So there's 4 suits. So 13 times 4 is 52. So this is the probability of getting a king, probability of getting a diamond, and then we have to subtract away the probability of both of those happening. How many king of diamonds are there in the deck? Just 1. So 1 out of 52 chance that already that happens. That's why we have to subtract it away, because we've already counted it twice. We have to undo the fact that we're counting it again. So that's going to end up being 16 out of 52, which I did reduce earlier. It's 4 out of 13 chance. And if you want to convert this to a percent, yes.
I'm confused.
Okay, what part?
1 over 52.
Okay, so in the deck, there's one situation where you can get a king of diamonds.
Oh, okay.
Does that make sense? Alright, so let's go ahead and try the next one. So in a school with 1,000 students, 550 students take Spanish, 650 take biology, and 300 take both Spanish and biology. What is the probability that a student selected at random takes Spanish or biology? So you're okay with finding a student who takes one or the other, which also means you're okay with them, if they take both, right? So we're going to find the probability of Spanish first. So what's the probability you find a student who just takes Spanish? Good, 550 out of 1,000. So if you just pick a random student in the hallway at this school, you have a 550 out of 1,000 chance that you're going to get one that takes Spanish. Plus, how many students here take biology?
650.
Good, 650 out of 1,000. And then we've already counted all the students who take Spanish and biology, so we have to subtract away what? 300 out of 1,000, because we've already it's like double counting them, in case they take both. So we do the math, we just basically deal with the numerators, and it comes out to be 900 out of 1,000, which means you have a 90% chance of encountering a student who takes Spanish or biology at the school. Yes?
Do you want us to put it in like percents?
I will specify if I want you to put it in a percent, but keep in mind on a test or quiz, if I ask you this question, the multiple choice could be given as a percent. So you do have to know how to calculate it. But no, if I don't ask, you can leave it as a fraction.
So you wouldn't put like it as a fraction and I guess in the percentage?
It's up to you. On your homework, I don't care as long as you know how to do both. But on the multiple choice, it's always it could be one or the other. So just be familiar with both. Any other questions about that? Okay. So let's go ahead and try the next one. Blank page. So on this one we have a spinner which has equally sized sections, and there's 20 spots on the spinner, numbered 1 through 20. Now why is it important they mention that they're equally sized sections?
So you know it's fair.
Yeah, so you know it's fair, right? If you go to like have you ever been to like a place where they have like the spinners and you can see that like one section's way bigger than the other one you want to win? And they do that because you have a lower chance of getting a smaller piece, right? They're not equally probable events. This one is equally probable for everything, okay? So, we're going to talk about this one, and we're going to talk about what it means. So, what is the probability of spinning a 2 or a 5? Well, we're not going to calculate it again, but do these events overlap? Do they affect each other? No, these events do not overlap. You can't do those two things at the same time, which means they are mutually exclusive, okay? I can't spell today. Don't spell like I'm spelling. Mutually. I was going to put multitude. I think I was going to write mutually exclusive. And then we're going to calculate this probability. So on this wheel, what's the chance of spinning a 2? 1 out of 20. And you're okay with also getting a 5, so plus, what's the chance of getting a 5? Good. So you add the numerators. It is, yes. So it's 2 out of 20, which is the same thing as 1/10, which is, yeah, 10%. So you have a 10% chance of spinning a 2 or a 5. Everybody good with how we got that? All right. So in this one, what is the probability of spinning a multiple of 2 or 5? So can these two events happen at the same time? Yeah. There's numbers that have multiples of both 2 and 5, right? So these events can overlap, and they are mutually inclusive. So when we say that they overlap, that means they can overlap. There are obviously situations where they don't overlap, right? So since they overlap, we're going to have to end up subtracting away the chance that they both happen. So first, multiple of 2. Well, a multiple of 2 is any even number on the board, right? So how many even numbers are there on the board? 10. So you have a 10 out of 20 chance of getting a multiple of 2. Plus, you're okay with getting a multiple of 5. So which of those numbers are multiples of 5? 4 of them. Good. So there's 4 multiples of 5. If you're not sure what those are, it's 5, 10, 15, and 20. Those are multiples of 5. Then we have to subtract away the situation where those things can happen at once, because we can't double count our probability. So which two numbers on that board are both multiples of 2 and 5? 10 and 20. So there's 2 times where that can happen. So we have to subtract away that additional extra count. And that will leave us with 12 out of 20, which is a 3/5 chance of that happening. Yep, exactly. So does that make sense why we have to do that? Yep, so you basically, the reason we subtract is you can't like you can't count something twice. You're counting it like twice basically if you don't subtract. So now we're going to talk about the complement, which we talked about last lesson. The complement of an event can be thought of as the probability of something not happening. So the probability that some event A will not occur is 1 minus the probability that the event will occur. So if I said to you there's a 10% chance it's going to rain, what's the chance it's not going to rain? 90. How did you find that? Yes, so you do this math all the time without realizing that you do it. You know what I mean? So you subtract from the percent all the time. So yeah, that's basically what you've already been doing for years now. So this says, what is the probability of not drawing a king or queen from a standard deck? So there's two ways to do this. I want you to look at example 1. What did we calculate in example 1? Yeah, we found the probability of getting a king or queen, right? So now we want to find the probability of that not happening, which is the complement of it happening. So what you do here is you do 1 minus the probability of getting a king or queen. And I know that I can rewrite 1 as 13 over 13. And then just subtract my numerators, which gives me I have an 11 out of 13 chance of not drawing a king or queen from a standard deck. So every time that you pick a random card from a deck, you have an 11 out of 13 chance of not getting a king or queen. Now here's another alternative on how to do this. How many cards in the deck are kings and queens? 8. So how many are not kings and queens? 44 out of 52, which reduces to 11 over 13. So that's two ways to do it. That makes sense? Okay. Let's move on to independent versus dependent events. So these events are going to be dealing with situations where we want two things to happen, one thing to happen and then another. So the more events that you want to happen in a chain of events, the less likely it's going to happen, right? If you go, if you know how people go to the casino, I don't know if you've like heard about this. You don't go to the casino yet, you're too young.
Cards. I feel like you too.
Not counting cards.
I was about to say, you're kind of teaching us how to count some cards.
I mean, eventually you will learn that. But the idea here is that, you know how they say people press their luck at the casino, right? Mm-hmm. The more you play, the longer, less your odds are that you're going to have all those events happen properly, right? So basically, the more that you expect to win, the less you're going to get if you keep trying to get more and more wins, right? You're going to have less the likelihood of all those things happening. So that's kind of where we talk about independent and dependent events. So oh my gosh, this is why I'm not an English teacher. Two events are independent of one another if one event does not affect the probability of the other event. Conversely, two events are dependent on one another if one event affects the probability of the other. The probability of two events, A and B, can be found by multiplying their probabilities. Okay? So this means you want one thing to happen and then the other thing to happen. So we have our independent events and then we have our dependent events. And we're going to talk about what this means, this slash. Okay? It represents the probability B occurs given A has occurred. So it sounds really complicated when I write it this way, but what it really means is if you are picking from a deck of cards, okay, you pick a queen, right? You had a 4 out of 52% chance, or 4 out of 52 chance in a fraction of that happening. Now, when you pick from the deck, what happens to the deck? It gets smaller, meaning that your probability changes, right? Because you're not replacing. So if you don't replace the card, the probability is changing each time. You're getting better and better odds because the deck is getting smaller. You have less to pick from. So that's the difference between an independent and a dependent event. So the more subsequent events, it changes the probability every time. So now we're going to determine if these events are independent or dependent and then find their probabilities. So, example A. rolling a 5 on a die, and then landing a tail on a coin toss. Are these events independent or dependent? Independent, right? The rolling of the die does not affect the tossing of the coin, right? Not unless you're doing it on the same table and they're hitting each other or something. We're not talking about that, but yeah, they don't affect each other. So what are the odds of rolling a 5 on a die? Good, 1 out of 6. And what about a tail on a coin toss? And we're gonna multiply these together instead of add them, because you want them both to happen. You don't want one or the other, you want both. And if you want both, it's gonna be less. So you multiply. 1 times 1 is? 6 times 2? Good. So if you were to roll a die and toss a coin, your chance of these two things happening is 1/12. So that's the difference between and or. Or you have more chances and you're restricting yourself a lot more. And that's kind of where it gets into when we talk about card games. This is how people end up losing. They don't realize how much it affects every time that you want another additional thing to happen. It really changes your probability. So, selecting a king from a deck of 52 cards after replacing the king in the deck and then selecting a queen from the deck of cards. So you take a king, you put the king back, and then you try to select the queen. Is that independent or dependent? You basically reset the deck, right? So it's independent. So if we reset the deck, these two events are independent again. So what is the probability of selecting a king? 4 out of 52. And then you want to select a queen. So times, what's the probability of selecting a queen? 4 out of 52. So if you want both of those events to happen, that ends up being 16 out of, I did this math earlier, let's check. Big number. Um, 2,704, which reduces to a 1 out of 169 chance. So you go from, this is one, selecting a king randomly is a 1 out of 13 chance. And then selecting another face card is a 1 out of 169 chance. So that's why it's so hard to get, if you're playing a certain card game, to get a bunch of face cards. See how your chances go way down when you want multiple things to happen. So let's try the next one. Selecting a king from a deck of 52 cards without replacing the king, and then selecting a queen. Independent or dependent? This one is dependent because you've changed the odds for the next event when you take the card away and don't replace it. Okay? So, let's go ahead and calculate our probability. So what's the probability of selecting the king? Good, 4 out of 52 times, now assume you selected the king. So we haven't changed the number of queens in the deck, right? There's still how many queens in the deck? But now, if you've taken away a king, how many cards are there? 51. So that's now 16 out of 2,652, which is equal to 4 out of 663. So your odds are better now, right? So your odds are better because you've taken one out of the deck. So it does increase your odds when you take cards out of the deck because you're having a less of a sample size, right, to pull from. So does anybody have any questions about this? Okay. So let's go ahead and do a marble example. So a jar contains 7 red marbles, 3 blue marbles, and 10 green marbles. What is the probability a blue marble is selected after selecting and replacing a red marble? So what's the first thing you're doing in this case? So it says after, so you're doing this first. So if you select and replace a red marble, what's the chances of getting that red marble?
It's still the same.
Yes, it is, but what is it literally?
7 out of
7 out of 20.
Good. So you have a 7 out of 20 chance of selecting a red marble. Times, now I replaced it, so does my total change? No. So 20 out of what to get the blue? 3 out of 20, right? So you select a red marble and you replace it, then you try to select the blue. So the chance of that happening is 21 out of 400. Make sense? Okay. So now, the probability of selecting a blue marble after selecting and keeping a red marble. So, what's the chance of selecting a red marble?
It's again.
7 out of 20, right? And then you don't replace it, you keep it. So now, if you're going to try to select a blue marble, what's different?
It's less.
Yeah, you have less options. And how many blue marbles are there to choose from? 3, because we didn't pick one originally, so there's still 3. So then we do the math, and that's going to be 21 out of 380. I think, yeah. So, is it better, do you have better odds if you take and keep or replace? Right, you have better odds. So, that's why they usually don't let you do that, because that increases your odds. So now we're going to do the next one. So choose a tile at random from the games list shown. You replace the first tile and then you choose again. What is the probability that you choose a dotted tile and then a dragon tile? Okay, so you replace the first tile and then you choose again. What is the probability that you choose a dotted tile and then a dragon tile? So what's the probability that you choose the dotted tile in the first place? How many dotted tiles are there? 4 out of 15. Okay, you choose the dotted, and then you replace it, and then you try to choose what? Good. How many dragons are there? There's. I think those are supposed to be birds. Those other ones. Yeah, it's 3 out of 15. So that's that reduces to 4 out of 75. So any questions about that? Yeah, it's kind of hard to tell what they are a little bit. I don't really know what that is. I think it's supposed to be like a bird. Alright.
Wait, what is the 4 out of 75?
Oh, I didn't. If you do the maths, like it's going to be 12 out of 285. I just reduced the fraction for you.
Okay.
Yeah.
Wait, so it was what?
I don't know. I did it earlier. 12 out of. Yeah, 225. And if you reduce 12 out of 225, it comes out to be 4 out of 75.
I have a question. So like,
Sure.
it says you replace the first tile, so you're just picking it up and then putting it right back?
Yeah, this part is really kind of pointless. It's just trying to say that if you like picked one up and put one back, it's not like changing anything about the that part of the question honestly is pretty like.
Yeah, I was like confused like what it had to do with it.
It doesn't, yeah. It was just kind of like trying to show you it didn't change anything. I know, kind of silly, yeah. Any other questions? Okay. So, without replacing the first tile, you select a second tile. What is the probability you choose a dotted tile and then a dragon tile? So basically, you're trying to choose the dotted tile first. So what's the chance of getting a dotted tile first? Good, 4 out of 15. And then you want to choose a dragon tile, but you don't replace it. So now your odds are out of what? 14. And how many dragon tiles are there?
4.
There's 3.
What?
3 dragons.
What about, wait, the other one was a Oh.
So this 12 out of 210 reduces to 2 out of 35. So any questions about that one? All right. Next one. 1 freshman, 2 sophomores, 4 juniors, and 5 seniors received top scores on a school essay contest. 2 names are randomly chosen to read the essays at the town fair. What is the probability that a junior and a senior are chosen? Okay. So, what's the probability of first choosing a junior? Good. But then,
And it's 5 out of 11.
yeah, go ahead. Good, so times the number of seniors, which is what? 5 out of how many now?
11.
11. Why did the probability go down in the denominator there? Yeah, we already chose out of the pool, so we're not going to have that person in the pool again, right? So that's going to be 20 out of 132.
Wait, what's the 22? Why is it 11?
Oh, sure. So I'll explain it again. So what happened here was probability of a junior and a senior. So the junior probability is 4 out of 12, but then you've chosen a student out of the pool, so now there's only 11 to select from. Does that make sense? Yeah, so there's only 11 students after that. So that's the chance of a junior and a senior. 1 freshman, 2 sophomores, and 4 juniors and 5 seniors receive, same situation. 3 names are randomly chosen to read their essays at the town fair. What is the probability that a junior and 2 seniors are chosen? So what's the probability of a junior being chosen? Good. And then choosing a senior? 5 out of 11. And then choosing another senior? Good. 4 out of 10. Good job. Yeah, because we took away a senior now, and we also took away another student, so it's out of 10. So you can do the math like on this whole thing, but I'll just tell you it comes out to be 2 out of 33. So I'm glad you understood that concept. Does anyone have any questions about this so far? You feeling good about it? Okay. So now we're going to talk about odds. So odds are a little bit of a different way to express a probability. And this is actually what they really use at casinos when they talk about a table game. They always talk about odds. So it's a little bit different. You're going to see how it represents a little bit differently. Another measure of chance that an event can occur is called the odds. The odds of an event occurring is a ratio that compares the number of ways an event can occur to the number of ways it cannot occur. So failure, so success and failure, S and F. So we don't represent it as a fraction out of the total. We talk about the success and the failure, okay? So, find the odds of drawing a heart from a deck of cards. So, how many chances are there for success of drawing a heart out of a deck of cards? 13, because there's 13 hearts in the deck of cards. And how many cards in the deck are not hearts? 39. So, your odds are 13 to 39 as a ratio, which you can reduce this ratio by dividing both items by 13, which means that it's a 1 in 3, meaning your odds are 1 in 3. You have a 1 in 3 odds of selecting a heart. So it's a very different way of talking about probability. So when they say 2 in 4, it's a different, it's not like a fraction, it's a different expression, okay? You can convert it to a fraction if you wanted to, but. So find the odds against drawing an ace from a deck of cards. So, against, we'll talk about how that changes things. What's the chance that you get an ace from a deck of cards? 4. And what's the chance of failure?
38.
48. Now the odds are against you, which means that now the failure goes in the front. So that's going to be 48 to 4, which reduces to a 1 to 12. So failure is 12 in 1. So this is how they express odds in a casino. Okay, they don't use fractions like we do, they use odds like this. So that's when they talk about, you probably have seen this before, that's what they're talking about. It's a different type of measure. So does anybody have any questions about this lesson at all?